Welcome back to Chapter 11, Part 2. I did fix that typo from before. So let's go ahead and dive into the next big idea that Mendel had, which was the second of the two laws that he figured out from just by breeding these pea plants. But he did something a little bit different. So the first time when he figured out the law of segregation, where alleles separate when you're making eggs and sperm, right? He was only looking at one characteristic. And anytime we talk about a cross that we're only looking at one characteristic, we use the term monohybrid, or we say monohybrid cross. So a cross between heterozygotes would be a monohybrid cross. Okay? So just kind of keep that in mind, that was what he did repeatedly over and over again, looking at one characteristic to determine his law of segregation. But he didn't stop there. No, he got very creative. And what he figured out was that if you look at two characteristics at the exact same time, you would be able to figure out how traits were inherited at the same time. So he identified his second law by following two characteristics. Again, we have to say at the same time. So in this case, we're looking at both color, right? The color is yellow or the color is green, but we're also looking at shape. So we can see that some of them are round, like there's round and there's round and there's round. But we also can see that some of them are wrinkled. And so you see those very wrinkly ones right here. And I'm just going to write rink because it's kind of hard writing on my little trackpad. So rink for wrinkled. So we're following these two traits at the same time. And we use the term dihybrid to refer to crossing two true breeding parents, looking at two characteristics. That's the word dihybrid. And dihybrid cross is a cross between the F1 dihybrids. So like you can kind of think about this, like how do you keep track of two traits at the same time? And one of the things that I like to do is look at each offspring in the cross and really pay attention to each trait that it has. So this one is both round and yellow. And I might write that inside the box, round and yellow, just kind of writing these down. Now, look, it's hard for me to write on this trackpad. I'm just going to admit it. You got big R, big Y, and I got little r and little y here. I would write out round and yellow if I were doing this on a piece of paper. So let's take a look at how you get to this to start out with. And it's not completely straightforward. And here's how your book presents it. And we'll talk about some of the math there in a second. But I want to step through this with you using a slightly different diagram because I like the way that this one shows off the gametes a little bit better. If you are big Y, big R, and just a second, and notice that the letters are in different orders on the one that your book is using. Whatever order you start with, just kind of stick with that order. So for this one sticks with the order of Y's and then R's. So we're going to stick with that order for this slide here. If you were going to follow the law of segregation, what that would say is that you have to put one allele into each gamete. Like you can't have two Y's in the same gamete. And you can't have two R's in the same gamete. But here's where the law of independent assortment comes into play. Because in a practical level, and this isn't the definition, but it is a very practical way to look at this. If you are trying to figure out how to make gametes, and you know that you're passing on a trait that's both color and texture, then you know your gamete, right? This gamete right here, it has to have a representation of the color and of the texture. So this is color and texture, yellow and round. And so the law of independent assortment really says I need to have one from each gene, one allele. That one allele, that's the law of segregation. But a one allele from each gene, that's where we start saying, oh yeah, we have to have one from each. Okay, that's independent assortment. And I could do these in different combinations. I could have this Y go with this R, or I could have this Y go with this R, and that's part of the puzzle that we're trying to figure out right now. In the green wrinkly one, remember that green is recessive, so they're going to get two little Y's. And remember that round is dominant, but wrinkly is recessive, so the little R stands for wrinkly. So this one is both green and wrinkly. And when we go through and making gametes, we have to follow the law of segregation. Only one Y can go into this gamete, right? But we also have to have one R because we're going to pass down both color and texture to the next generation. So if we cross these two together, we're going to get these hybrids. Big Y, big R, little r. Right? And all of the offspring of a cross between these two are going to be big Y, big R, little r. So if we take, and they're all identical, so if we take one of those offspring and we made it to another in a dihybrid cross, we're going to come up with a bunch of different gametes. Now, I'm going to draw those out here for you. So let's start out, let's just do it over here on the side. Big Y, little y, big R, little r. And we're trying to figure out all the possible gametes. And the way you do this is it's something like this version of FOIL that you've been learning, you know, in algebra class, basically all of your adult life. And the way you do this is say, oh, well, this big Y, again, that's supposed to be a big Y, can go in a gamete with this big R. So I'm going to draw it more like a big Y just to make things easy. And then it's going to go into a gamete with this big R, right? So that's the first two together. And then we could do like the outer ones next. We could do big Y could go with little r, big Y goes with little r, and then we could do the inner ones next. Little y goes with big R, right? And yes, you write it in that order because you want to stick with whatever order that you're starting with. And then last, little y goes with little r. So first, outer, inner, last. It's very similar to your math class, but it's not across a multiplication sign. So just kind of be aware of that. It's the way you make gametes within a dihybrid. So if you put that into a Punnett square, you actually have to do a 4 by 4 Punnett square. And then once you start making gametes, like this big Y, big R could fertilize with this big Y, big R, and you get big Y, big Y, big R, big R. And you just keep going along there until you are completely filled in all 16 squares. Now, we're going to make a connection here between Mendel's law of independent assortment, where we're looking at dihybrids, and the law of independent assortment that we thought about when we were thinking about this when it came to meiosis. So it's the same concept, it turns out. Even though Mendel didn't know anything about chromosomes, he came up with the idea of what it must look like. So I already showed you this picture. I showed you this picture earlier where I just kind of described how you could get all these different variations in the possible gametes. Here it is with a much simpler version of it. This is kind of like a dihybrid where you've got two different genes. Here's gene 1 and gene 2, and they're on, they're like, we could say this is kind of big Y here, and this is little y, and this is big R, right? And this is little r, like that. Okay. You could and you could end up with this thing where the big Y goes with the big R, right? Big Y in the same cell with big R, because that's the big Y and that's the big R. And this would be the little y and the little r. Or same over here, but let's do a little mix and match. Like the big blue one, that was y, right? Big Y. That's big Y. And the little, and the big red chromosome over there, that would be the little y. And the little blue one, that's big R. And the little red one over here, that's little r. Little r. So in this set of gametes, if they separate, remember that homologous chromosomes separate or segregate during meiosis 1. You'd have big Y, and you'd have little r. And here you'd have little y and big R. So you could get all 4 of those possible combinations that we saw here, right? Those are the 4 possible allele sets that you get when you make gametes. And if you look right here, it's the same idea. Big R, big Y, big R, big Y, big R, little y, little r. There's that one right there. And so forth. Big Y, little r. That's that one right there. Right? So the law of segregation, the law of independent assortment that we learned about in meiosis absolutely applies to what we learn with Mendel. Here's the thing, though. The law applies to genes on chromosomes that are not homologous. What I mean by that, or also they have to be far apart on the same chromosome, but these ones are not homologous. So the R gene is not on the same chromosome as the Y gene, right? They're on different chromosomes. So we say they're not on homologous chromosomes, the R gene and the Y gene. If genes are located really close to each other on the same chromosome, that kind of changes things around a little bit, and I will talk to you about that. But for now, when Mendel was thinking about the way things worked, he figured it all out. He just got really super lucky that most of the traits that he looked at when he was doing dihybrids were on different chromosomes. So lucky him. We can do this, we can look at probability of how you pass down traits mathematically. We don't have to always do Punnett squares the way that I've shown you this. There is just applying some laws of probability and to segregation and independent assortment that are useful. And the way I want you to think about this is if you were tossing a coin. Remember that the tossing of a coin, if you're tossing a coin like so, you flip it once and you flip it again. The outcome of the first flip has no impact on the outcome of the second flip. No influence at all. So that's the same way that genes on different chromosomes don't affect each other. They don't impact each other as long as they're on separate chromosomes. So we can use 2 separate rules to help us figure out probabilities. So the first rule that we're going to learn is the multiplication rule. And the multiplication rule says that if you have 2 or more independent events, if those are going to occur at the same time, like you're flipping 2 coins at the same time, that you just multiply the probabilities together. So you can see this in our monohybrid cross. You've got half of the sperm are big R and half of the sperm are little r. Same thing for eggs. Half of the eggs are big R and half of the eggs are little r. So if we just multiply 1/2 times 1/2, we get 1/4, right? And it doesn't matter which box you do this. It's 1/2 times 1/2 is 1/4. But look right here. These 2, they end up being the same. They end up being both big R and little r, heterozygous. So that's interesting, because even though you have a 1/4 chance of this egg meeting up with this sperm, you also have a 1/4 chance of this egg meeting up with this sperm, and you end up getting the same result. So that's going to bring in the addition rule. And the addition rule says that the probability of any two or more mutually exclusive events occurring at the same time, like occurring, you usually add them together. So you can use that to figure out the results of how many of the like F2s from monohybrid cross will be heterozygous instead of homozygous. So you can also do this with multiple characteristics, like if you're looking at like a dihybrid cross. So you can do this for monohybrid crosses, you can do it for dihybrid crosses. It really is just remembering when you're going to use the multiplication rule and when you're going to use the addition rule. So let's just back up a real quick second and say that we used the multiplication rule when we were trying to figure out the probability of this sperm meeting up with this egg. But we use the addition rule to say, oh, but there's two different ways that could happen, and I want to combine them. So that's going to be add 1/4 plus 1/4 is 1/2. So that was for monohybrid. And let's see if we can apply this to a dihybrid. So let's think about the probability of this genotype here, big Y, big Y, big R, big R, making a specific kind of gamete. So they have a 1 in 4 probability of having an offspring that's big Y, big Y. And if this doesn't make sense to you, we can go back and kind of fill in the blanks a little bit, right? So we have a big Y, big Y, big R offspring. Or that's what we're trying to end up with, that's what we're trying to get to. Big Y, big Y, big R, big R. And we have our parents are big Y, big R, little r. And we know that 1/4 of those gametes are going to be big Y, big R. We know that because we just looked at it when we were doing it up here, right? 1/4 of those were big Y, big R. There it is right there. So, and we also know that 1/4 of them are going to be, from the other parent, are going to be big Y, big R from both parents. You got a 1 in 4 chance of making the big Y, big R gamete. And so basically what you need to do is you just multiply them together. So you have a 1 in 16 chance of having an offspring that is big Y, big Y, big R, big R. Now what's the probability of having a big Y, little y, big R, big R? Again, if we go back, we can remember that this is where we're going to go to. If we want big Y, little y, big R, big R, there's a couple of different ways we could get that. We could use this gamete right here. We could also have this gamete right here. Yeah, does that make sense? So there's two different gametes that we can be looking at. So you could get big Y, big R, but you also have to have a little y, little r, and you can get that from either set of parents. So, so again, the way that you might want to think about this is, what are your chances of getting that big Y, little y? And that's about 1/2. Again, just looking at the monohybrid cross, that heterozygous, that's a 1/2 chance. Yeah? So 1/2 chance of getting that big Y, little y, but still 1/4 chance of having that homozygous. And so you just multiply those together. 1/2 times 1/4 is 1/8. So you got a 1 in 8 chance of having a big Y, little y, big R, big R. Using math is really useful to do, but you could also just do the Punnett squares, and until you get really familiar with them, it's easy to just kind of just fill out the Punnett squares. It is very nice to do the math, so I would like to encourage you to practice doing some of that math, and we'll try to do that when we're together in lab as well. So leaving the math behind for just a little while, we can also kind of wrap this idea up by saying that inheriting things can be simple from monohybrid crosses. They can also be a little bit more complicated with the dihybrid crosses, but the basic principles are always going to apply with looking at both monohybrid and dihybrid. The basic principles are always going to be there. But you know what? Mendel didn't know everything. And he got a lot of those basics absolutely right. And we're always going to be following the basics. But there are times when alleles are not completely dominant or completely recessive. Like this idea of blending. It's not blending, but there is sometimes something in the middle. So what do you do? Or what do you do if a gene has more than 2 alleles? Like, what about blood type? I mean, that has more than 2 alleles. What do you do then? Or what do you do when you have one gene, but it has many different effects on the phenotype? So Mendel didn't know everything, and we're going to spend the next bit of lecture talking about the things that Mendel didn't know so much about, going beyond Mendel.